Okay, so just so you guys know, the correct answers were elephant, ellipsis, apple, and collar. How'd we do? 1 for 4?
2 for 4.
2 for 4? Anybody do better than 2? Huh. So you guys, how many possible outcomes were there for each of these questions? Here's a hint. The answer is not 5. Because not one of you said, I got, that would mean 20 possible outcomes on this quiz. Nobody said I got a 20. What did you actually measure? You got 2 out of 4. 2 what? 2 correct answers out of 4 questions. Right?
Yeah.
Is everybody with me? Okay, so today we're going to talk about 2 different kind of discrete random variables, and all of these discrete random variables match some very specific settings. Okay, do you guys agree with me that what we had here are repeated trials? And in fact, each question was a trial for you, right? Like you looked at it and you said, I'm going to guess an answer for each one. Now, there were 5 options for you to guess, but at the end of the day, when I circled the elephant here, there were only 2 outcomes. What did you say? How many of you guessed elephant? So you guys are right, and everybody else was wrong. So really, even though there were 5 answer choices, there are 2 outcomes. Success or failure. That'd be good? What else is pretty cool about this question? You have the same probability of success each time. That's where the 5 answer choices came in. That's the probability that you guessed correctly. Everybody good? And lastly, not only did we have repeated trials, we kind of had like a set number of 4 repeated trials. 4 questions, each question a trial. Everybody good? So if we wanted to, we could actually make a tree diagram that kind of follows what this would look like. Does that kind of make some sense? Okay. And so this first branch did you get question number 1? What was your outcome on question number 1? Right? So correct or incorrect. And then this next set of branches is what happened on question number 2? We getting a basic feel for what I'm trying to map out here? Okay, so in terms of outcomes, there's a lot of corrects and incorrects. And my guess is each of you could trace different paths along the way, right? You could say like, oh, I got the first one right, and then I got the next one wrong, and the next one wrong, and the next one right. And that would be your path. Is everybody with me? Okay, now, for each question, what was the probability of getting the question correct? 0.2, 1 out of 5. Okay, and then, so if it's a 0.2 chance of getting the question correct, there's a 0.8 chance of getting the question incorrect. we feeling so far? Now, when we talk about these distributions called binomial distributions, the intent for us here is to see like all of those probabilities being the same on every set of branches makes for some known predictable patterns within how those probabilities are going to fall. Is everybody okay? Like, while complicated, and if I went much more than 4 trials, I'm pretty sure you guys would throw me out the window, right? If you're going to do that, can you wait till there's like a bouncy house out there for me to fall on so I don't get hurt, okay? Like, doesn't this feel like something, I don't know, a piece of software should be able to do quick? Great. So I'm going to show you the software, how to do it, okay? But I need us to see that it works because we have some patterns that are going to exist as we do this, okay? All right, so this correct right here is different than, say, this correct right here, right? Both of them are somebody getting their last answer correct, but they mean different things, right? What does this, what student can get to this path? What would it mean about the student they got to this correct answer? They got them all right. So that, and in fact, when I got done, you guys were all like, ooh, I got 1 right. I got 2 right, right? Can we go through and say how many correct happened on each one of these branches? So for example, to get to this branch, how many did you get right? 3. Are we good? So let's count up the number correct on each branch. All right. Are we good? So, the number of correct answers is 0, 1, 2, 3, 4, right? Now, we're going to kind of work our way through how to get to this, okay? So, 4 correct here. How many different ways can a person get 4 correct? This is the only one, right? Of all the branches, this is the only one that got 4 correct, yeah? So there was one way that happened. What about getting 3 correct? How many different ways can a person get 3 correct? Excuse me. Oh, wait, I did that. How many different ways can a person get 3 correct? 4, great. 2 correct?
6.
We get the basic gist here. Now, so there's just, and that kind of makes some sense if we work really hard at it. Are you with me that getting 1 correct is equivalent to getting 3 wrong? Right, so it makes sense that you get the same amount of ways. Now, does anybody believe that this should have the same likelihood as this? No, because if these were all 50-50, sure, no problem. Okay? By the way, do these numbers look familiar to any of you guys? Pascal's triangle? Have you guys seen Pascal's triangle before? All right, so real quick, Sir Bunsen Pascal. Pascal was a mathematician way before he was a chemist. In fact, he's the father of modern probability. He was the first guy that put 2 and 2 together, that just because there's 2 possible outcomes doesn't mean they're both equally likely. History lesson. You guys didn't know you were getting history in stats class today. Okay, so can we follow this branch real quick? If I ask you what is the probability of getting 4 correct, based off of that multiplication rule we did the other day, wouldn't that mean I do 0.2 times 0.2 times 0.2 times 0.2? It was 0.2, I think. I think it was one short. Everybody good? So to find that probability, I would do 0.2 to the fourth power. I got it. And likewise, to get 0 correct, even though there was only one way to do it, what would I do? 0.8 times itself 4 times. I think. I should probably double check that. It's been like a day. Okay? But those ones are easy because there's only one way to do it, okay? So now I want to look through and say, all right, what is getting 1 correct? So let's look at those branches. So to get 1 correct, I have, this is the first 1 correct. I have a 0.8, 0.8, 0.8, and a 0.2 at the top there. So for this one, I have a 0.2, and then I have 0.8 3 times. And then, I'm going to jump to this one next, right here. 0.2, 0.8, 0.8, 0.8. So that one is also 0.2 and then 0.8 3 times. We seeing it? And if I do this one, I have 0.8, 0.8, 0.2, 0.8. Is it? So if I'm getting 1 correct and 3 wrong, I'm going to have 1.2 and 3.8s. Are we all seeing it? So what happens is there's like this lovely pattern that exists. And likewise, if to get 3 right, it's going to be exactly the opposite, right? Like I have 0.2, 0.2, 0.2, 0.8, 3 0.2s and 1.8. Is everybody feeling pretty decent about where this is coming from? Okay, so, and likewise, to be one of the ways that you got 2 correct, you had 2.2s and 2.8s. And if, let's say instead of it being 80-20, it was 70-30, or it was 4 answer choices, so 0.25 and 0.75, these patterns would be the same. The probabilities would change, but the patterns would be the same, right? Okay, so in this setting where my probabilities stay the same all the way through, there's a lovely set of patterns that makes this pretty easy and manageable. Okay, so we can figure all of these out. I'm pretty sure this one's 0.4096 again. Everybody good? If I add all these up, what do you think I'm going to get? 1? Cool? Great. All right, now, if I wanted to, could we build a histogram of this? Sure. But if I want to, could I find the mean and the standard deviation using that frequency list that we talked about on Wednesday? Yep. All right. So, this is an example of a binomial random variable, and anything that has 4 trials with a probability of 0.2 would match this model. Okay, so it's not. So let's say I have a couple who's getting ready to have children. Okay, and in their children, they know they're going to have exactly 4 children, and the probability that given their genetic makeups The probability that their children have brown eyes is 0.2. Very good? Pretty unlikely. All right, so what is the probability for children, probability of 0.2 that they get brown eyes? What is the probability that exactly 3 of them have brown eyes? I think it's 0.0256. Because that's the exact same model. In fact, in order to figure out that tree diagram, I would put brown and not brown for their eyes, and it'd be the exact same picture. Everybody good? All right, so a binomial model is one where we have repeated trials, called Bernoulli trials, but you don't need to know that. Within those repeated trials, they are binary. They're, in other words, 2 outcomes, success or failure. You have a set number of trials. Now, that in this case, we had 4 trials. We could have 10 trials, 15 trials, 100 trials. It doesn't matter. But it is a set number, okay? And that each trial has to have the same probability of success. In other words, each of these, in order for these to work out, they always have to be 0.8s and 0.2s all the way through that tree diagram. Okay? How are we feeling so far? Great. So let's turn the page real quick. So, some symbols we will be using when we deal with binomial variables. N is going to be my number of trials. P is going to be my probability of success for a single trial. Q is my probability of failure. X is going to be the designated probability to find. So, next what I'd like you to do is show you some stuff in the calculator, because unless you guys want to draw one of those tree diagrams for every single one of these. No? We don't want to do that? Oh, okay. All right. So just a reminder, we're going to let x equal our number correct. Okay. And just some quick reminders of some things. Okay? So on your calculators were built with kind of some intuition involved. It's not stuff that's randomly placed in there. Come on. Okay. So the next part I'm going to show you because I'm not always going to be here like when you're working your homework or whatever. Okay. So as you're looking at your calculator, you have to know kind of how it's built, and it was built intentionally. Okay. Now, the binomial distribution is a known predictable probability distribution, and there's a whole bunch of known predictable probability distributions. We've already talked about one of them. We haven't used the calculator for it yet, called the normal distribution, right? The normal distribution is very predictable, 68, 95, 99.7. Binomials are very predictable. So, if you stare at your calculator long enough, which I'm going to encourage you to do real quick, see if you can't find something that might help you figure out where to find these known predictable distributions. All you have to do is stare at you don't even have to press a button. You just stare at those buttons. You're going to find something that might jump out at you looking for distributions. Anybody see anything? Distra. Does everybody see Distra? Where's Distra? Vars. Second vars. So go ahead and hit second vars. And you won't be able to see it, but my calculator is a little bit better than yours when it comes to what parts. I can see it much further down into the list. You can start to feel you can see maybe, if you keep scrolling down, the binomial distribution. You've got two options, binom PDF and binom CDF. Everybody good? If I do binom PDF, it is going to tell me the probability that x is equal to some number. So if I want to fill in this box right here, I want to know what is the probability that x equals 0. Everybody good? So I'm going to choose binom PDF, which is A. You scroll down to get to it. Go ahead and hit enter. Mine's going to look a little bit different than yours. What's the first thing it's asking you for? Trials. What should I put? This is the previous page. 4. Yeah, we had 4 questions. Next thing it asks you for is the probability, which is, what was the probability of success for each trial? 0.2. Next, it's going to ask you for the x value. That's whatever probability it is you're trying to find. So if I'm trying to fill in this box right here, I want to find what is the probability x equals 0. So I'm going to put in 0 for x. Are we good? I'm going to hit enter. 0.4096. Isn't that what we got on the previous page? So we don't need that tree diagram. We did the tree diagram for you guys to see what this is built from. Your calculator can do that tree diagram real fast. That's basically what's going on here. Everybody feel good? So if I did the same thing, except for now I'm going to pick x equals 1. I also got 0.4096. Let's do one more. Let's do x equals 3. Oh, I meant to do x equals 2. Hold on. Everybody good? How are we feeling so far? Still feeling pretty decent? All right. So if I can recognize that something is binomial, I can do these real quick probabilities, okay? Now, if I asked you what is the probability, well, let's figure out what does this one do, this binom CDF. Let's look. I'm just going to throw this, I'm going to throw x equals 3 into that one just to see what happens. Everybody good? You think I'm going to get the same answer? Different function, right? So assuming a different answer. 0.9728. What do you guys think happened? It gave me the probability x is less than or equal to 2. So, this probability is binom PDF. This combined probability is binom CDF. Everybody good? So, your calculator has 2 functions for binomials. PDF is for when x is equal to a number. You're trying to find exactly what number. CDF gives me the probability x is less than or equal to that number. We still feeling okay? If I gave you this table, and then we just, again, figured out that the combined probabilities of 0, 1, and 2 are 0.9728. If I asked you guys, what is the probability that x is greater than or equal to 3? Could we find it? Are you with me that these two and this should add up to what? 1. Because it's every possible outcome. So to find this, I could really just do 1 minus that 0.9728. So your calculator can only do the either x equals or x is less than or equal to. But if it doesn't give me the right thing, I can do some manipulation to get there. Is everybody okay? So let's look at some more examples. I got a dice. I'm going to roll it 20 times, and x is going to be the number of times I roll a 3. Okay? So I got to decide, first of all, if I roll that dice, I got multiple trials, right? Do I have a set number of those trials? How many times am I rolling that dice? 20. So if I can write n equals 20, I have a set number of trials. Okay? All right. Now, the next thing I need to know is, do each of those trials have the same probability of success? Each trial is unrolling, right? And the question is, do I get a 3 or not? Binary, I either get a 3 or I don't. What's the probability I roll a 3? So, I'm sorry?
1 out of 6. I give you a decimal instead of a...
Oh. Yeah, because your calculator, you can actually type in 1/6. This is going to be more precise. We're going to use that. Are we good? Just for what we're putting in the calculator. So we're not putting in a rounded answer.
Okay.
If I can write an n and a p, we can say that, yes, this is binomial. Okay? Now, so now if I want to know what is the probability that I roll a 3 exactly 4 times, so I said it's binomial. So now I'm going to go to my calculator, right? I'm going to pick binomial, so I got to choose. Am I going to pick binomial PDF or binomial CDF? What do you think? PDF. Okay, what about this tells me PDF? It's that equal sign. Equal sign means PDF. Are we good? Fill in so what am I putting in for my trials? 20. My probability of success, 1/6. My x value would be, trying to find the probability x is equal to 4. So I put in 4. What is the probability I roll a 3 at most 5 times? What does the phrase at most mean? 5 is the most. So it could be 5 or less. So x is less than or equal to 5. All right, so am I picking binomial PDF or CDF? And how do I know? CDF. What is the probability we roll a 3 less than 8 times? Can I put this into binomial CDF? Why not? CDF is the probability x is less than or equal to. That and less than or equal to, right?
Could we not just put 7?
So what we say to ourselves is, what, could we rewrite this in an equivalent manner? Which outcomes are less than 8? 7, 6, 5, 4, right? Like, because there is no 7.5 times, because this is discrete. So this we would rewrite this, the probability x is less than or equal to 7. And then put it in. What is the probability that we roll a 3 at least 7 times? At least would be 7 is the least, yeah? So that would be greater than or equal to 7. Oof. Can I put that in binomial CDF? Can I rewrite that as a less than or equal to? So here's what we got to do, y'all. We got to do exactly what we did up here where we subtract from 1. We have to be really, really careful. So we are going to do 1 minus the probability that x is less than or equal to, but what we choose to put right here, we have to be super careful about, okay? So what I'm going to say is, I'm going to start by asking myself, which outcomes are in fact greater than or equal to 7? 7, 8, 9, 10, right? And so on. I got to take away the ones that are not greater than or equal to 7. Which outcomes are not greater than or equal to 7?
1, 2, 3, 4, 5, 6.
6 and lower. Is everybody with me? So I'm going to do the probability x is less than or equal to 6. And this one, once I have the less than or equal to, that's when I can throw into that CDF. All right, let's look at one more example and we'll take a break, okay? Suppose 40% of statistics students will major in business. We take a random sample of 15. So I have n equals 15. I have p equals 0.4. Do we see that this is binomial? What is the probability that more than 10 students will be business majors? So, first of all, you guys, if I were to ask you how many would you, excuse me, how many would you expect to be business majors? Sample of 15, 40% overall. How many would you expect? 6, right? So if I'm asking what is the probability that we get more than 10, are we expecting a high probability or a low probability? If I'm expecting 6, more than 10 doesn't feel very likely. The reason I'm pointing this out is especially with greater than questions and we have to do that 1 minus, thinking this through can be helpful because sometimes people forget steps, okay? All right, now, if I'm saying I'm going to take away the outcomes that are not greater than 10, Which outcomes are not greater than 10? Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9. What about 10? Is 10 greater than 10? So I'm going to take away the probability that x is less than or equal to 10. So the reason I'm pointing this out, here, greater than or equal to 7, I took this down by 1. Here I didn't. You guys see, this is why I'm pointing this out, okay? And it's because if I'm including these 7 here, I'm not including it here. I'm not including the 10 here, so I need to include it here. Is everybody good? All right. And from there we get an answer. I'm not really worried about the answer. 1 minus... Oh, nope. Yeah, problem. And look, I would call that a very small probability. Which, if I forget to do the 1 minus, which happens sometimes because people get so focused on putting that binomial in your calculator, you get 0.99. Is everybody with me? Like, that's why I think there's value, because it's really easy to, like, focus on getting this number and forget to subtract it from 1, okay? Thinking through, what am I expecting to get as my answer to make sure I'm not forgetting that step, because it's pretty easy to do. It's not that I'm speaking from experience of teaching this particular topic for the past 15 years. All right, let's take 5, and then we'll finish. Because binomial distributions are known and predictable, there's quick formulas to find the mean and standard deviation. They go like this. The mean is NP. You guys, this should be intuitive. I know this because I asked you guys, how many would you expect of those 40%, 15 students? And we said 6. Nobody argued with 6. That felt right? Because the mean and the expected value are the same thing. You take your number of trials times your probability. That's your mean. That formula, by the way, is on your formula sheet. You do not need to memorize either of these, okay? You do need to know what the different symbols are, okay? My standard deviation is the square root of NPQ, N15, P.4. A reminder, Q is your probability of failure. So if P is 0.4, what's Q? 0.6, because the two of them should add to 1. All right. So if I were to ask you, would it be unusual to get, if I take this sample, to only get 1 business major, or 8 or 14, can you guys remind me what was usual versus unusual? 2 standard deviations. So I'm going to take my mean plus or minus 2 times my standard deviation. And that gives me what is usual, close to the mean. So, would 1 be considered usual or unusual? Unusual. 8, usual. 14, pretty unusual. All right, that's binomial random variables. So, I could ask you about random variables where I'd give you just a table. Okay, that's what we did on Wednesday. I could give you something where I ask you to recognize that it's binomial. That's another way I might ask you about it. The last one I'm going to ask you about is something called the Poisson distribution. And the Poisson distribution talks about how many times something occurs over an interval of time. Okay? So X is going to equal a number of occurrences. You guys, it's 2 R's. And the occurrences need to be uniformly distributed over the time interval. So, it is discrete. So, an example is, I might say over a class period, Tatum's going to blink on an average. Over a 45-minute class period, Tatum's going to blink 62 times. That's the average number of blinks. Every time, not 62. Every good? That's the basic crux of this. Okay? And then I might say, oh, in this class period, what's the probability Tatum blinks more than 70 times? Tatum, I hope you don't mind me picking on you. Every good? Make sense? All right. So we have an average, and then the standard deviation of the Poisson distribution is always just the square root of the average. So you'll be given the average. The standard deviation is just the square root of that number. Again, that formula, just double checking it, but I'm 90% sure that formula is in fact on your formula sheet for the standard deviation. Okay? So you'll never have to worry about the formulas for mean, standard deviation. Are we good? Let's look at an example. All right. Suppose the mean number of tardies for Grandview students in a 5-day week is 58.8. That seems incredibly low. I would imagine there's more tardies than that in a week, but I made it up. So, all right. Find the mean tardies per day and the standard deviation. So, if the mean is 58.8 for the week, what's the mean for a day? Take my 58.8. That 58.8 is the mean for a 5-day week. What do you guys think I should do? I'm going to divide it by my number of days. And so the average number of days, or number of tardies for a day, is 11.76. I should ask Mrs. Berlin what the answer to this is. You would think block days would be half as many, right? That would be really interesting. What about the standard deviation then? The square root of 11.76. Okay. Would it be unusual for there to be 15 tardies in one day? Are you guys with me that 15 tardies would be on the large side? So what I'm going to do is I'm going to take my mean. I'm not going to worry about the plus or minus. I'm only going to worry about the plus. Not unusual because it's not more than 2 standard deviations above the mean. All right, now, turns out that the Poisson distribution, much like the binomial distribution, is this kind of known, predictable probability distribution. So if I say, what is the probability that there are exactly 10 tardies in a day? I want to find the probability x equals 10. So now what I'm going to do is I'm going to say, well, how do then... I'm going to go back to that distributions menu because now I know it follows a Poisson distribution. And I'm going to say, is there anything in that distributions menu that might help me with the Poisson distribution? And right below the binomials, we have Poisson PDF and Poisson CDF. Are we good? So if I'm trying to answer this question, do I want to pick Poisson PDF or Poisson CDF? If it's strictly equal to. PDF goes with equal to. It doesn't matter if I'm talking about binomial or Poisson, PDF is still the probability that x is equal. So I'm going to choose Poisson PDF. Oh, hold on. It's going to ask you, for some calculators, it might say this, like mine where it has that lambda, or it might say mu. Both, no matter what, it needs to know the mean and the x value. Okay, so my mean was, and this is in a day, 1 day, so I'm going to put 11.76. And my x value is going to be 10. What is the probability that more than 15 tardies occur? All right. What should I pick here? Eventually, I will pick CDF, but the CDF only tells me x is less than or equal to. So I got it. This is going to have to be a 1 minus. And which ones do I want to take away if I'm doing greater than 15? So let's see.
Oh, wait, no.
15. So is the 15 included here?
No.
Then I need to include it here. Are we good? Now I'll pick Poisson, whatever, CDF. How are we feeling, okay? So the rules for PDF, CDF, the same. So the trick will be, which distribution are you using? Okay? Let's do another example. On average, 20 calls are received at a customer service center between 9 a.m. and 10 a.m. So if I say what is the distribution, that means you're going to tell me the name and the important characteristics, okay? So the minute I see this, 9 a.m. to 10 a.m., the minute I see that time frame, that's my clue that this is going to be Poisson, with the mean being 20 and the standard deviation being the square root of 20. How are we feeling so far? What is the probability the call center gets fewer than 14? What are you thinking? That's equivalent to the probability x is less than or equal to 13, which is 0.066. What's the probability that the center gets exactly 22? What are we getting? .077. All right, trying to trick you on the next one. In fact, I'm kind of trying to trick you twice. What is the probability that the center gets at least 24 calls between 9 and 9:30? What's one way I'm trying to trick you? It's not the same time frame. So what is my new mean?
10.
I cut my time frame in half, so I got to cut my mean in half because I'm going to get half as many calls in half that time frame. All right, and then I want to find the probability x is greater than or equal to 24. All right, so in this case, is the 24 included here? So I cannot include it here. So this has to be less than or equal to 23. And before we put this in, y'all, are you expecting a big number or a small number for this? Small. Right? You're expecting to get 10. More than 24 would be insane. So, if I'm doing this, right, I'm expecting a small number and I just got 0.9998. I forgot to do the 1 minus. This brings up another point. Y'all, if you tell me that the answer is 1.2, I'm not even giving you partial credit. Why would I get really mad at an answer of 1.2?
Because that's 120%.
Probability can't be bigger than 1. Okay, my calculator gave me 1.2, e negative 4. I'm fine with you saying 1.2 times 10 to the negative 4th. That is fine. But if you don't if you just write down the decimal without recognizing that this is a probability and cannot be bigger than 1, I'm not giving you partial credit. Is everybody understanding me there? Because you need to at least know, if I'm asking you to find a probability, it's got to be smaller than 1. Everybody good? All right, once you guys do this last one, we'll call it a day. How'd we do?
Why is it 10 and not 11?
Oh, it should be 11. And I typed 11 on my calculator. Yeah. Because hopefully we caught that my mean here would be 5 because it's only 15 minutes instead of the whole hour or the half hour. Shorter time frame, so you got to be... And I'm telling you right now, if I'm going to try and trick you on the test, that's how I'm going to do it. And you can assume that you're going to have to do at least one, find the probable x is bigger than or equal to, less than, like all the different variations of what you're going to be throwing into, like that PDF and CDF stuff. Somewhere between the binomial and the Poisson questions, I'm telling you that is going to happen. Yeah.
lab due next week? As it probably says it on it. Oh,
Thursday.
okay,
This lab goes quick.
okay.
So it would be pretty reasonable, especially you have 20 minutes now, you could get a head start on the unified homework. It would be pretty reasonable that you get both done in the block period next week.
And we'll have time to do that.